So I'm going to talk to you now about fast alignment, okay? Let me get the laser pointer out here, okay. So I just want to start off by talking a little bit about computational complexity. Now, we were talking about that a little bit last time in terms of when we talked about multiple sequence alignment, maybe scaling it to many sequences. So if you just think about the sort of dynamic programming matrix, and this is the classic one that we went through with the Needleman-Wunsch type of thing, where you could kind of think about how many operations you have to do, to do this. Well, you can kind of see that with the size of the input sequences, if this sequence is length m and this sequence is length n, the amount of stuff you have to store here and the amount of sort of cells you have to go through just to fill this initial matrix, you have to go through here n squared times, right, to fill this thing, okay? Now, there's an additional complexity too, actually. You might realize that when you come here, as you go up the matrix, like as we're going up here, you have to scan back all of this sort of black band here to find the best match to connect it on. And the size of this thing also is going to scale too. So obviously, if you have really long sequences, it's going to get very big. So actually, the complexity of this, as I've drawn it, is n cubed, okay? So it's going to scale with the length of the sequences roughly cubically, okay? So if you sort of double the length of your input sequences you're thinking about, you're going to go up by a factor of 8 and stuff like that. So now the thing is, there's a little trick that you can do to make this a little bit faster, and that is you can waste a little bit more memory. You can make another matrix, and what you can do is when you sort of are at here, you can kind of pick the best match you had up to this point. You can kind of cache the thing that led to the best match or something like that. So now when you go to the next thing on, you only have to compare what you've added on to this band relative to that best match that you've cached, right? You don't have to rescan the entire black band here. You see what I'm saying? So if you cache the best match that you have, you just have to compare what you add on to that. So now you've removed the scaling with the size of the sequences to that. So now the complexity will go down to n squared, okay, back down to n squared. Now you might say, oh, n squared, that seems very fast, that seems great, but it turns out that's, in the context of doing a gargantuan number of these calculations, it's actually not very fast at all. So it wouldn't scale very well for a lot of the things that we do with contemporary computers and next-gen sequencing and stuff like that. And, so a lot of what people have done, since the 1970s to now is as the data has exploded, they've spent a lot of time thinking about how to make basic sequence alignment things faster, and there's a lot of machinery put into that, trying to make things go faster and faster. And one thing also I'd like to point out here is I think when I show you the complexity here, remember I was kind of quickly saying, oh, it wouldn't work to try to do this for 3 sequences. Well, think about what would happen for 3 sequences. You'd be making this cube now. Okay, so now there's a cube you're building. It's not a matrix or tensor or whatever you want to call it. And just the size of the stuff that you're doing is going cubically, what I'm saying? And now if you did it for 4 sequences, it would go up n to the 4th. And you can see that if you wanted to do a multiple alignment of 40 sequences, you'd have n to the 40th. You couldn't do that, that easily. It would just scale terribly with the sequence sizes. And that's why for multiple sequence alignment, people have to use these heuristic approaches. So let me go forward here. Oops. Here we are. So now I'm going to tell you a little bit about what people have done with developing kind of fast alignment approaches. And sort of, like I said, you can kind of see, with the increase in data, there's been a kind of increase in, or not increase, but there's an evolution of different approaches that people have done, in addition to computers getting faster. And I don't know if you people remember from the first set of slides that we had where we talked about the scaling of, the Moore's law and how the data was scaling in genomics and computing is scaling. So in addition to computing is getting faster and the data getting bigger, people are also doing, have to do algorithmic gymnastics. And so every couple of years, they kind of really rethink how they're going to do this. And as we're going to talk about today, they first, they first did the, I guess, manual thing, then they moved to the Needleman-Wunsch or Smith-Waterman n-squared type approaches. Then they moved, as we're going to talk about, to sort of hashing approaches, and then they moved to these even more convoluted types of things that we're going to talk about, like the Burrows-Wheeler transform and stuff like that. And that's actually what I just said here on this thing. So this is kind of the history of people, essentially using different algorithms. And I should point out that you don't get something for nothing. What's happening in a lot of these algorithms, as we're going to talk about, is that they're trading speed for sensitivity. They're not in some senses, they're not really as sensitive to find things. And actually, so there's a sort of counter progression, and that's a little bit what we talked about last time with, say, PsyBlast or multi-sequence alignment, where people develop more sensitive searches that are even more sensitive than the original sorry, my screen just popped here. That are more sort of sensitive than the original Needleman-Wunsch approach, but they are slower. Okay, and so they're, a lot of times you have to make that kind of trade-off when you're doing things. Okay, so first let me tell you about the first classic way people were making things go a bit faster, and this is just making up a simple hash table of words in the query sequence. And this was popularized in the 1980s by this Bill Pearson. Again, I think the key is people tend not to use this particular software that much now, but I just think the main idea is to understand the concept of how this works. What you basically do is you get your short words in your query sequence. You look for all the short words in the query sequence, and you make a big hash table of them. So you can retrieve a given k-mer or short word from your query sequence by just looking it up in the hash table. So for instance, you might look up ACT in your query, and it will just tell you where it occurs in your in the query sequence. And obviously the amount of hashing you're doing depends on the sort of k-tuple or k-mer size. You could imagine doing this for 3s, for 4s, and so forth. And you can sort of see that you're getting a coarser version of the sequence when you're using bigger k's. And here's a picture of your sequence with your different k-mers. So now what you can do, which is a little bit easier, is you have your two sequences now, right? And here's your query and your one you're matching up to in your database, right? Now what you can do is you can hash up one of these sequences, and then you get your hash table where all the things are. And then you can look through the other sequence, and you can just directly say, oh, if I have an AAA here, where does it match there? You're just doing a hash lookup. Okay, so you're just doing that's very fast. And so you can fill in really quickly exact matches on the diagonal. Okay, so you get all those little diagonal bands really quickly. And then, so then the sequence alignment becomes a little different. You don't have to find those diagonals. Now all you have to do is kind of stitch them together or something like that. And so that's what the FASTA program does. It basically, you get all these things, and then it has some sort of joining process where it stitches these long diagonals together, and it looks through all the long diagonals to get the best diagonal match. Now, of course, if you don't have something on a diagonal, if there's not a perfect match, imagine you had, like, for instance, in your query, you had AAA, and in the database, it was, it was a non-exact match. It was AATA. That would not be incorporated into the diagonal. You would see that as the hash wouldn't find it. But maybe it deserves to be kind of a diagonal, because if you were aligning it and you had a substitution matrix, you would be getting a pretty good score for following along that path. So you're losing that, right? Because you're doing the exact hash lookup, you're losing that. So be it. So now I'm going to tell you about BLAST. This is a program that's probably still used a bit. For a long time, it was the most popular program in bioinformatics. And it was, I think it's probably it might still be the most cited paper in biological science, period. It was, and it's cited because, they built a really nice software for this. And then this is the early days of the World Wide Web and so forth. They built a really nice server that was coupled to databases. And so people would constantly, if they had a sequence, just simply paste their sequence in to this server, and kaboom, it would give you all the matches in some nice format. And this was very very popular for many years, and so people used this a lot. So how does this program work? It's similar to FASTA. It was very inspired by that, but a little bit different. It indexes the query, and then what it does, which is a little bit different than FASTA, is it finds all the hash matches between two sequences. That if you have your database sequence and your query sequence, is going to find all the hash matches. But it doesn't really try to stitch together the hash matches the way FASTA does, because that required a little bit of dynamic programming, and that was a little expensive. All it does is take that best hash match and tries to extend that match. And I'll show you how it does that. And that's it. And then to make it a little bit more sensitive, it allows sometimes the hash match to be a little bit more generalized. Like, it doesn't maybe all the time have to be an exact match. It, allows a slightly more generalized hash match. And so that's it. And then what it does is it has the notion of these best hash matches. And I think the lingo that it uses was maximum segment pairs or high scoring pairs. And there's no gaps allowed in those at all, and in the extension of them. But one of the nice things about this is that because it's such a simple matching approach, it's just looking for a big chunk of diagonal that's extended. There's a very nice and sophisticated scoring system that was developed for this based on extreme value distribution statistics that was developed by Sam Carlin. And I'm not going to tell you about that scoring system. I used to go over it in class sometimes, but I'm not going to go over it so much now. But basically, the nice thing about it is, in addition to giving you a score, it would give you some, like, a p-value, or how likely you were to get that score in some randomized version of the database. And that p-value was very useful for people when they originally were thinking about big databases and how to think about the value of the score and so forth. So let me tell you a little bit about how that this works. So it's pretty simple. So you have your query. You're going to look up all the places in your database sequence that with the hash that match, and you're going to, for instance, find it matches here, and then you're going to find all the best matches, just single hash hits from your query to your database sequence. And then you're going to take the best one, you're just going to extend it. And so you're going to grow the sequence, and you're going to say, oh, this matched, pretty well, this matched exactly. You can maybe add on the neighboring valine tyrosine, valine tryptophan match. Maybe that gives you a little bit of stuff. And then if you add on to the next thing, you don't really get any value. And you just kind of add on until you get no more contribution to the overall match. And that is, that's it. And this thing just takes order n. You know what I'm saying? This whole thing just scales with order n. So it's much, much faster than the order n squared that you have in the traditional Smith-Waterman database search. And then this just shows you know, what you might have if you were searching a database. So you'd find all your best matches, and then you'd extend one, and you'd get all these best matches. This is your highest scoring segment, and then you would get the statistics over this for doing this. And of course, this is going to scale with your database size, of course. So you're going to have to compute this this number in relation to the size of the database. And then they developed, you know, there's endless varieties of this. They went on and developed a gap version of this program where you could get two pairs and it would stitch them together really quickly. And, you know, it was kind of a halfway house between the FASTA approach and the BLAST approach and so forth. That's what that's just what this shows here, just kind of stitching those things together. And I think the key aspect of the key reason they didn't go all the way to the FASTA approach is they could all the time have very nice statistics, like I said, based on this extreme value distribution statistics for the matches, and also for these sort of extended matches too, which it turned out actually the most useful thing about BLAST were the statistics. Okay, so now time goes on, and this is all happening maybe around the time of the sequencing of the human genome in 2000. And then, you know, subsequently to that, they sequenced more and more. They obviously sequenced the human genome, but then they developed, of course, next-gen sequencing. And people sort of start to think about, well, what could we do to make things a little bit faster? So one thing they can do, you can imagine doing right off, and I think this was done by the BLAT program, is that instead of hashing the query sequence, you could hash everything in the database. So, you know, you have your big database, right? So you have to pay a huge price here. You're going to go through your database. You're going to find, you're going to hash everything in the database. And so you can look up, you know, for instance, if you have AAAT in your query, you can now look up all over your database really quickly where it occurs. But of course, that's a huge hash table you have to build up. And it means that, you know, you can't just start your sequence run right away with a bunch of sequences. There's this huge pre-cost to build this massive hash table. But once you do that, it's much faster. And this was done by the BLAT program, which I think was developed by Jim Kent. And well, that's actually what I just had here. So it builds an index, unlike BLAST, which builds an index of the query, BLAT builds an index of the database. So the next set of things that people would do is they would use this thing called the Burrows-Wheeler transform to make things a bit quicker. Because believe it or not, when we moved to next-gen sequencing, and this is, you know, sort of in the early 2000s, there was too much even for this hashing the database approach. And so people use this yet more sophisticated way of kind of encoding the sequences to look them up very quickly. Now, I'm not going to tell you in detail about the Burrows-Wheeler transform because it's very confusing, and I frankly don't know my way through it in detail. I just want to give you a sense of a little bit of the gymnastics that are going on, just so you kind of get a sense of, oh, well, we started from the Needleman-Wunsch. This is where we are now. And so most of the programs that you would use now would tend to actually use these approaches, though, like I said, it's a little convoluted what they're doing. So what they're doing is opposed, for instance, if you're matching the genome there or the database, they're not going to do a hash table like BLAT did. They're going to do this Burrows-Wheeler transform. the thing. And it's this has to do with kind of cyclically permuting all the little k-mers and then kind of sorting and compressing them. And then once you build this somewhat complicated data structure, you can take, of course, each read or thing that you're wanting to match and then look through this, what's called a prefix tree or something like that, in very fast linear time. That's the basic idea. And then just kind of quickly, I'll show you what I mean by what these things kind of do. Here's an example, sequence A. What you're going to do is you're going to take your sequence and you're going to cyclically permute your sequence, okay? And you sort of generate this somewhat complicated structure from doing that. And then you take the last column from this sequence is a little confused. And you're going to make another sort of sequence from that, and you'll use that in the matching. Now, like I said, I'm not explaining this very, sort of in detail. I just want to give you a sense of the gymnastics that you're kind of going through. It's a little bit more complicated than what I guess we started with. So in any case, that's what happens with your Burrows-Willow transform. And then the key thing I just want to point out is this trade-off that we have. So, we started out with the Smith-Waterman. We talked about, sort of hashing, hashing the query, hashing the database, and then this more Burrows-Willow transform gets faster. You lose sensitivity, okay? The other way around is, we talked a little bit about that, to move into the world of multi-sequence alignments, where you take one sequence and you kind of, as opposed to taking that sequence, you generalize it and make a kind of pattern from it. And that's, of course, what we talked about with the profiles. And we didn't go into details, but to some degree, the same thing happens when you take a sequence and you kind of put it into a hidden Markov model. And there you get a more sensitive matching, but it takes more time. It's more expensive and it takes more time to search. And then just to close, we might think about what would be the what would happen next. So I think that there's sort of, I think, two things that are kind of coming up that are maybe for the future. Now we have what we call third generation sequencing, the PacBio and so forth, and this sequencing has a particular quality that the reads are no longer so short, but they're very full of errors. And so there's a lot of discussion about how to make new aligners that really accommodate this type of data. And then another kind of interesting thing too is a kind of privacy aspect is, a lot of times when we start to think about doing personal genomes of identifiable people, we want to keep the data, the genomics data, maybe safe and secure. So we might want to think about how we can do some of the matching to with encrypted data, in some way, to either having the database be encrypted, the query sequence be encrypted, and so forth. And so these are some challenges for the future. Okay, so that's the